Okay, so we are slowly moving towards the actual thing of neural networks. Now, this is the chapter where we are dealing with single layer perceptron. Slowly, we will go to multi-layer. Now, in last class, we have seen how to find out this discriminant functions for different classes. So, we initially saw this is class 1, this is class 2, then we draw a line between these two classes, and uh, we could differentiate between two groups. Now this concept was extended to say k number of classes. Okay. And for doing that we require the discriminant function, say g1, g2, and so on up to gkx. And how to obtain these things, we have seen that we will use the basic principle of minimum distance from a given test sample. So there will be a sample which we want to classify, and we have different, say, such prototypes belonging to different, say, classes like this, and we find out distance between these prototypes and the test sample. So whichever distance is minimum, we say that the given input belongs to particular group. So this was the simple thing, and we developed this equation GIX equal to XI transpose X minus half XI transpose XI. So this was our conclusion in previous class. And then we could implement this very easily in the form of a neural network. So these were the k neurons representing k different classes. So k different classes means k different prototypes. So each prototype was actually residing over here, and along with some extra terminal, that is minus half xi transpose xi. So these are actually the prototypes. So like x1, here it will lie x2, and so on. Here it will lie xk, and these are the weights associated to implement this portion of this line. Okay, so this is a constant that is implemented by last node, and this xi transpose, that is prototype value, that was kept here. So this was x1, this was x2, and so on. Somewhere here there will be xi. Along with that, it's constant. So like that, we are implementing k different functions, gk's, and we take the maximum response for a given input and declare its index as our output. Then we took one example, 3-class example. Say these are prototypes P1, then P2, P3. Then based on minimum distance principle, you can see if this is P3 and P1, here will be the point. From this point, distance to say P1 and distance to P3 is same. Okay, so this becomes my decision boundary or decision surface actually between two classes, that is class 1 and class 3. Similarly, we can find out a decision boundary here between class 1 and class 2. Then we have a boundary between class 2 and class 3. So like that, we have implemented very easily by knowing only 3 prototypes based on the respective class data. So we actually take the mean of that and then create this prototype. By knowing that, our design is immediately ready. So that is very simple actually. Then we took one example and just saw how these boundaries are developing, how these things are actually implemented. So these are the actual boundaries you can see between, say this is a boundary between class 1 and class 2, and these shaded things are actually the discriminant functions representing different classes. So there are three classes. I have three surfaces representing this. Okay, then we will now go to the actual, say, problem. What is linear problem and what is a non-linear problem? What we saw in previous class or right now was a linear problem. I could draw a line or a plane between two classes and then I can identify them. So this is like drawing a line here on a 2D surface. So I can draw a line and I can separate this class 1 and class 2. Now if I have a class which requires such kind of a boundary, so this is class 1 sample, these are all class 1 samples, and these are all suppose class 2 samples. So I cannot draw a straight line to do this job like here. Okay. Or for example this group where this is say class 1 and class 2 is submerged in class 1. So this is class 2 which is inside class 1. So I cannot draw a line like this and solve this problem, which I could solve with the help of a perceptron or with the help of a minimum distance principle. So if you see typically this problem, what will be centroid of this crosses? So if I take all these crosses and find out centroid, so possibly it will come inside somewhere here. And what will be the centroid of all these samples which are within this small circle? That will be also residing somewhere here only. Okay, so if both are actually ideally suppose overlapping, class 1 and class 2 prototypes are overlapping, then you cannot differentiate between class 1 and class 2. So such kind of problem you cannot solve with minimum distance approach. Okay, so these are typically non-linear problems. These are typically non-linear problems, so you cannot solve with the help of normal techniques. Now, before we solve that non-linear problem, we will see a new way of learning. What we have done to find out these prototypes, and then we implemented with the help of so-called neurons. But can I obtain these discriminant functions automatically? I am not interested in calculating this g of x. So I don't want to calculate or obtain this gix. I want a ready-made solution. That means somebody will give me this gix automatically when you present the pattern. Say I want a black box like this. I will be presenting the patterns one by one, and this gix is developed automatically. Okay, I don't want to calculate prototypes and then use minimum distance principle and then do all those things. So that is a manual procedure. I want something like this. I will present input pattern, then I will define the desired response. Okay, I will present say a pattern x1, and then I will say okay, this belongs to class 1, do whatever you want to do inside. Okay, then I will present pattern 2, then I will say okay, it belongs to class 3, learn somehow within yourself. So that is what I want. Okay, so this is the next step. And we will do this with the method called as non-parametric training concept. So learn from data directly. That is the concept. Non-parametric doesn't mean that there are no parameters. In fact, parameters are dependent on data. There are parameters to set and they are dependent on your data presentation. So somewhat it's misleading, but the name is given in context with you can say pattern recognition using statistical methods. So those who have done that course, they are knowing that when you present the data, I assume that it is normally distributed, then I find out mean, then I find out variance, and I say normal distribution is mu and variance. So these are actually the parameters we compute from data. So these are parameters computed based on data. First of all, we assume a model on my data like this, that it is normally distributed, and then I find out mean and variance for that. Okay, so it becomes parametric method in that sense that you are just interested in computing the parameters of distribution. Now here we are not using that kind of technique or that kind of approach where we are assuming some data distribution and then finding out parameters of that. Okay, what we assume here is that data is separable with the help of line or a plane. So that is our basic assumption right now. Now let us see what is this. So if you try to understand what exactly this approach is, then your further study in neural networks becomes very simple. Okay, so whatever I am telling you right now is the core of neural networks. Now suppose this is a feature space. It means that it is the space of say x1, x2, x3 and so on up to xn. Right now I am taking a 2D example. Here x1 and x2, these are two coordinates. That means the input pattern which is coming to the system consists of two variables, that is x1 and x2. That means I have measured say two features for my problem, say maybe height and width. Okay, so this may be height and this may be width. Now what I do, I want to classify two objects, suppose, with the help of these two measurements. Okay, so there is one object here which has less height but big width, and this side if I take height is more and width is less. Okay, so you can take any object like this and you can take variety of those objects and then you get different measurements like this, maybe something like this, and this is other class. So what do? You draw this line so that this becomes one class and this becomes other class, and this line is represented by this particular equation, w transpose x plus w n plus 1. It's like y equal to mx plus c. So what I can do, I can take these things to the left hand side, y minus mx minus c equal to 0, and this thing I will now write in this form. Okay, so when I generalize this concept, then there are many parameters here, so I will collect all those parameters and I will call that as w vector, that is weight vector. So weight vector multiplied by x plus the constant, that is c. Okay, so this wn plus 1 is nothing but your c in y equal to mx plus c. Okay, so if you just take 2D example, I can write this as w1 x1 plus w2 x2 plus w3 equal to 0. So what is w1? w1 is here plus 1, w2 is minus m, and w3 is minus c. Okay, so this is what is the comparison between these two equations. So it is just the way of representation. For simplicity, we write as W transpose X plus W n plus 1. So if you have one more dimension, then I think this concept will be clear. I can write for 3 dimensions. So W1 x1 plus W2 x2 plus W3 x3 plus W4 equal to 0. So this is the plane equation for a 3D space. Now this W4 is playing the role of C, that is constant. Okay, and these are the variables of this space. Now if I collect this part of your equation, then I can write this as W transpose X plus W4 equal to 0. Now what is W in that case? W in this case is collection of all variables, coefficients associated with the variables. So it will be W1, W2, W3. And what is X in this case? It will be X1, X2, X3. So when I take W transpose, this will be W1, W2, W3, like this. Okay, then you can multiply with X. So resultant will be this box again plus W4. So this equation W transpose X plus W4 and this equation, say A and B, they are exactly the same equations. And a generalized version of this I write like this. Okay, so you can see this is a 3-dimensional weight W1, W2, W3, and W4 is this component, constant. So if I say my W vector is n-dimensional, so W1, W2 like that, if I keep on adding, then Wn, then the extra term, that is constant, becomes Wn plus 1. Okay, so this complete equation is W transpose X plus Wn plus 1 equal to 0. So that is what I am writing here. Now the basic concept that we are going to use is, we are calling this line or plane equation as the discriminant function. So we are using it as a function. How I can use? So when I say, so this is a key thing, you just concentrate on this. When I say this is my line or a plane equation which is lying over here, so what is meaning is, throughout you travel on this line throughout, say from this minus infinity end to this plus infinity end. If you walk on this line, what is value over here? If I call this as g of x, if I say g of x is equal to W transpose X plus Wn plus 1. Okay, I'm just not putting it equal to 0. I'm just calling this as g of x. What is value of g of x if I travel on this line or a plane? So it is g of x equal to 0. This line equation is that. But if I just move away from this line, suppose I am standing over here. Now if I put this value of x into this equation, when I take any sample, suppose here, whatever may be value of x, if I put into this equation, it will give me equal to 0. If I take anything, suppose from this location, and put that value of x into this equation, so it will be giving you something else than that 0. 0 will be received by you only if you take any point on this line. If you take other than that, you will not get 0. So there are two options. You will get a positive output or you will get a negative output. You will get some positive number or you will get some negative number. So when you will get positive number, when you will get negative number, so thumb rule is that thumb rule is for remembering. Okay, so you can show why this is happening. But right now, just remember, when you take the coefficients of that line or plane, and if you plot that, suppose I take the coefficients, say W1 and W2 here, and if I try to plot, and suppose this is the direction of that vector, then that will be the positive side of the line, or that g of x. And if you take the opposite side of that, it will be negative portion of that function. So how it looks, suppose this is the line. This line is, say, w1 x1 plus w2 x2 plus w3 equal to 0. Say this is x1, this is x2, and this is that particular line. And sorry, I should write this as x2 from back side, and this is my g of x on third axis. So this is the function which I am looking, and I will say g of x is equal to this term. If I plot this g of x by varying all possible values of x1 and x2, what are the space variables with me? I have two variables, say x1 and x2. So if I take all possible combinations of this, then you will get such a plane which has some slope. If you can see from this side. Okay, so what is value of g of x on this particular line when you travel on this? So here your value of g of x is equal to 0. Okay, value of g of x is equal to 0. Now if you take any sample other than that, suppose I take this sample, then what you will obtain? You will obtain g of x. So let me draw neatly. You will obtain some value here. Okay, some value here. So this will be your g of x. Suppose I take this as x1, then this will be g of x1, and this will be some positive number. You can see here, this is positive axis of g of x, and negative axis of g of x is this side. So if you take any sample from this part, then if you project it on the plane, you will get some negative value of g of x. So if you look from side, this is your g of x plane, and you can see these are x1, x2 axis from side. So this g of x plane has three parts. This is where this g of x is equal to 0. So this is where this line is actually located. So I am looking towards this line from, say, this part. Okay, this is the direction where I am looking now, and this is visible to me from this side. I hope you can imagine that. So this is the portion. If you take any sample like this, any sample, so it will cut to the positive side of the plane. If you take anything, it will cut or give you positive output. If you take any sample from this side, it will cut to the negative portion of your g of x. So g of x is negative for these samples, and g of x is positive for these samples. So I have made three things: g of x is equal to 0, g of x is greater than 0, g of x is less than 0. Okay, Now what I say, when g of x is greater than 0, say my input belongs to class 1. When g of x is less than 0, my input belongs to class 2. When g of x is equal to 0, I can't decide. So it is the decision boundary. So my decision boundary between two classes is this line. So this side is class 2 and this side is class 1. How I will find out? So I know that what is g of x for my problem. So for a given input x, you substitute value of x into this equation. If you get a positive number, just say that my input belongs to class 1. If you get a negative number, you say my input belongs to class 2. This is how this perceptron is designed. Now for example, I have a feature space x1 and x2. Okay, so what I do, I just randomly assume a decision boundary like this. I don't know the solution. Where is class 1? Where is class 2? I have even not seen the samples, training samples. For that particular thing, suppose this is my neuron and this is a 2D case. So what I'm going to do is I'm going to assume this is my input x1, x2. So this is x2, this is x1, and for the constant term, I will add here 1, and this will be w1, w2, w3. So since for my problem, I don't know the solution, where I should draw this line initially. Okay, I have even not seen any sample. So what I do, I randomly assume. So note this, randomly assume weight vector for a given neuron. So I just put some numbers here, w1, w2, w3, and assume that this is the line which is being drawn because of this random assumption. Okay, and then I present pattern number 1, say x1, which actually belongs to class 2. So before I start my problem, I will say I want for class 1 g of x should produce positive response, and for class 2 g of x should produce negative response. Okay, so that is our requirement, and then I draw this line which I have assumed randomly, and then I find out the list of samples which I want to learn. The first sample is lying over here, and then what I do, I collect the coefficients of this line and draw this w vector. So w vector is indicating this side of the line as positive, and obviously the bottom side becomes negative. Now you are being presented x1 which belongs to class 2, for which you want a negative response, but you can see your line is here, line is lying over here. That's why you will get a positive response. So your line position is not correct. So you need some adjustment of this line so that you start getting correct answers. Now how you can do that? So you can tilt this line, so which was lying earlier here. You can change the position of line to this position, new position. Okay, this is a new line. So that is what is happening in your learning. So there is a delta W calculation. So you have W new equal to W old plus delta W. Okay, this delta W addition to the old weight will shift this line from this position to this position. Okay, so suppose you keep this thing here, you have shifted the line here. What will happen? Again you take the W vector and plot. So this is the direction of positive response, and this is opposite is the direction of negative response. Now you stand to the line, say line is here, on the line g of x is equal to 0. Now this side of the line is now negative and this side of the line is now positive. Now what you want for x1? You want negative response for x1, and since you are below the line, you will get negative response. Okay, so that is what you want. You are getting a negative response and you have properly adjusted that line position. Now that was the space called as feature space. Now you can do the same thing in augmented weight space. Now what is augmented weight space? So we have this W transpose X plus Wn plus 1 equal to 0. So this was our equation of line earlier. So what I do now, if I write this properly, so this is W1, W2 and so on up to Wn. So this is W transpose. Then X is X1, X2 up to Xn plus Wn plus 1 equal to 0. Now what I will do is I will try to accommodate this Wn plus 1 into this vector. So if I do that, I can write this at W1, W2, Wn and Wn plus 1. Okay, so I've added this last term here. Then to match the dimension, what I have to do is I have to write this as x1, x2 and so on up to xn, and I have to add 1 here so that dimensions are matched equal to 0. So again you will see that product of these two, that is this vector, is now called as augmented weight space. Augment means you are adding some dimension. So this is added. Now similarly we are adding 1 to the feature space. Okay, so this is n plus 1th dimension. So I will call this new vector as y now. Okay, and this as same as w. So this new w and this y, so w transpose y equal to 0. So this is our equation in augmented weight space. Same equation I am rewriting in this form. But what is beauty of this? This line will always pass through origin. So why, you can check that. But remember, this W transpose y equal to 0 will always pass through origin of this augmented space. So there is no constant actually added. So if you add some constant, the lines will shift. Since there is no constant here, the constant is shifted to augmented space. So this will always pass through origin. This W transpose y is always passing through origin. Now this is a weight space instead of feature space. So what is done here? Remember, I am plotting now in weight space. So this is my W1 and W2. These are parameters to be adjusted for given input. given input is x1, so it will be suffixed with 1, so that is converted into y. So if you plot this y vector, say lying over here, a line perpendicular to that will give you the decision boundary automatically. Now this line has positive side this in this direction and negative side in this direction. Okay, so immediately you can plot this line by knowing the feature vector y, augmented feature vector y. Now suppose I have this input as y1, and these are the weight variables or the variables which we want to adjust, and by chance this is the random assumption of weight. So initial weight is randomly assumed, suppose here. Okay, and the input pattern is y1, which is in this direction. So what you can do is you can draw a line perpendicular to this vector, so that this w transpose y is equal to 0 on this line. Okay, since there is a 90-degree, you can see that this is going to happen. Now for this particular line, this side of the line is positive and this side of the line is negative. If your input y belongs to class 1, you want that it should produce positive response, or it should lie in positive half of the plane. But you see, the weights are right now lying in the negative side of the function g of x. Okay, if I call this as g of x equal to this, then this side is negative, this side is positive. Since your weights are lying over here, what is your output? Output is negative, and you want actually positive. Since your input belongs to class 1, you want positive response. So in this case, how to adjust your answer? If you keep new weights from this side of the line, any weight from this side of the line, you can choose this weight, or this weight, any weight which is above this line, your product w transpose y is going to be greater than 0. Okay, any weight if you choose from this bottom side, w transpose y is going to be, say, negative. I want positive, so what I do, I take this weight and move in this direction and go to this side, and I put this weight here. So what is my direction? You can see this is the direction of my input pattern. I can move this weight from this position to this position. I can move this weight from this position to this position, but it will take long time to travel here compared to this and this. So which is the best path? Which is the best path? This is the shortest path to travel, so that you will change your wrong answer to correct answer immediately. So you can see I am traveling in this direction. Okay, so I was here with a wrong answer, then I will move in this direction so that I will get the correct answer. So what we do, we got a negative answer. So to increase g of y, that is equal to w transpose y1, we prefer a gradient direction for weight changes. Now what is gradient direction? So we have this W transpose Y1. So if I take gradient of this with respect to weight, so if I differentiate this with respect to weight, partial differentiation, so that is you can say with respect to W1 first, then W2 first, or I can write here gradient vector if you want. So this gradient of W is like this. So this will be dou of W1, so W transpose Y1, okay, then dou of W2, W transpose Y1, and so on up to Wn. So if you expand this W transpose Y, then it will be W1 x1 plus W2 x2 and so on up to Wn plus 1 as usual. So if you take now differentiation of this equation with respect to W1, what will happen? This x1 will appear, others will go. Okay, so if you do that for all w's and collect that vector, it becomes the y vector, which is the collection of x1, x2 up to xn, and additional is that constant. Okay, so if you take this fastest path, this was my line and this was my y1. I was standing here with initial weight w1, then I have to move to this side. The fastest is the perpendicular direction, not other directions. I can even move like this. Okay, so I want to go to the solution fast, so I should travel this perpendicular to the line, which is gradient of this function. Gradient of what function? G of x W transpose y. Okay, so I will travel from this position to this position. And how I will do that? So this weights vector is added some delta W, this vector, so that new position is obtained. So W2 is equal to W1 plus C into Y. Now why this C is coming into picture? This is called as learning constant. I can move in this Y direction heavily, or I can move with a small step. So to control this step size, I can take different values of C. If I put in general for C equal to 0.1, then it's a moderate value. So I will be moving my weights from this position to next position, then next position, and so on. And I will keep on presenting different weights to that particular neuron. So this is the opposite case where your initial weight is lying over here, which is producing positive response. Your input is y1. This is the direction of input, but class is 2. So to make this thing correct, that means for this particular input, what is your output? Output is positive, since your weights are lying over here. Now you want to change your weight from this position to this solution region. So you want to move in this direction as fast as possible so that you will cross this line. So again, you will travel in negative gradient direction. So again, it's a perpendicular thing. So you will be taking the gradient. Gradient will give you this direction, but since you belong to class 2, you will go in opposite direction. So you will now subtract from the weight. So note that when you will subtract, when y belongs to class 2 and you are producing positive response, you want a negative, so you will subtract so that you will cross that line. So we have now two options for the weights. You have to add sometimes, you have to subtract sometimes. When you will add, when you want positive response and you are getting negative output, so you will add this delta W. In opposite case, you want negative response but you are getting positive output, so you will subtract the weight. So that thing is that you have to have your weights in proper position. When your weights are, say, in wrong position, you have to adjust them. So that is the basic theme behind perceptron. So combiningly, you have this equation, say W new is equal to W old plus or minus Cy. Okay, so here you will see in perceptron learning rule, when to add and when to subtract, that headache is removed by the term D minus O. Okay, so C into D minus O into Y. So that if you do, then this care of subtracting or adding is automatically done. So that is removed by C into D minus O into Y. And you will take old weight and you will get new weights. Okay, so stop here. Let us stop here. We will see in more details next time. So meanwhile, you find out your queries and you can ask me at the beginning of next class.